Good evening, students. I'll start with the class. In the previous class, we were discussing the thermodynamic processes. So we had seen the main four types. That is isothermal. These are the thermodynamic processes. Isothermal, then was isochoric, isobaric, and adiabatic. Okay, so second one we'll consider now in detail, which will study is the adiabatic process. Order doesn't matter in which process you study. Third one would be isochoric. Fourth one will do isobaric. This we know that temperature is constant. Here we do no exchange of heat to the environment. Isochoric will be volume is constant and here pressure is constant. So previous class we had seen the isothermal process and we had derived the work done for isothermal process. Now we'll see adiabatic process. In adiabatic process, we make sure that no heat is lost to the environment or no heat from the environment comes into the cylinder or whatever object you are taking. Okay. So in order for no heat to release or no heat to come in, you know that the system has to be an insulated one. System is insulated from the surrounding. Therefore, heat absorbed or released is zero. It's a very fast process. Okay. Delta Q is zero for this. So what basically they do is the same example we will take the cylinder and the piston. Now this part is insulated. Everything will be insulated. Okay, you can write perfectly insulated walls in it. These are fully insulated. Now what they do is they make sure no heat, there is no external supply of heat in this process. Usually what we do, there are two ways to increase the internal energy of the gas. One is to do the work on it, one is to supply heat from outside. Now here there is nothing coming from outside to in or inside to outside. Okay, no heat exchange takes place. So now what they do is first thing, suppose consider now this I'm compressing from here to here I'll bring. Okay. So when I'm compressing, what is going to happen? The gas molecules will get compressed. This will be compressed. So under compression, what is going to happen? The molecules will try to come closer. The volume is decreased now. Okay, as it comes closer, the internal energy will always increase. Under compression, whenever any work done is on the system, then the energy will always increase. Now, what is going to happen? This will the gas gets heated up. Okay, or gas gets compressed. Okay, so energy will increase. Heat will increase. Therefore, temperature will rise. Now, this temperature is not lost out in the environment. Okay, so how you can change the temperature or increase the energy by compressing the gas. Am I supplying any energy outside? No. Is any energy from here going out? No. Still, I can make the temperature increase by just compressing the gas. Just putting the piston, compressing, the heat of the gas will increase. Same way, without any exchange in the heat outside, what I'll do, I'll release this piston up now. From here, it will go up. This side, it was coming here. Now it might go up. So that would be expansion. Then expansion, what is going to happen? Gas will expand. So as it expands, the gas will cool. Okay, so heat is reduced and therefore temperature will reduce. Okay, you can just write this in your own words and keep. Whenever gas is compressed, heat will rise, temperature will rise. For expansion, whenever gas will expand, the gas will cool down. The gas will cool down and heat will decrease, therefore temperature will decrease. So this is a adiabatic process. This has to happen very fast. Huh? Right in, so whenever you can continue after this, whenever work is done on the system, its energy increases or heat energy increases. So you can take example of a adiabatic process. You can take example of a flask. Thermoflask. You know that your flask is insulated from all the sides. And now consider you have put some hot tea inside. Now, what they say is whenever you try to move this flask or shake this flask at a very high speed, no, the tea inside no will become slightly hotter than which temperature it was before also. Okay, if you try to move that liquid inside the thermoflask very quickly, very fast, slightly, not so much different, but at least slightly it will become hotter than which it was before. Why? Basically, by moving or shaking the thermoflask, you are doing work on the liquid. Okay, so whenever any work is done on a system, its heat energy will increase. You can write that example and keep. And we want to slightly heat it up more. We shake the flask, that is, we are doing work on the system. So we'll see what is the thermodynamic laws is. The thermodynamic laws is delta Q is delta U plus delta W. For adiabatic process, there is no heat exchange, so delta Q is 0. So this will become 0. So the work done is nothing but minus so whenever we are doing work on the system, it's actually considered on the system is negative. It's the same thing. So energy. Okay, as per the formula, work is minus delta U for adiabatic process, where U is your internal energy. We'll see what happens for ideal gas. Adiabatic process of an ideal gas. Normally, we know that for an ideal gas, pressure into volume is always constant. Okay, pressure into volume is always constant. The same thing it is for ideal gas. Only extra will be here represented by a small r. Just put a small r here. That is always constant. So what is this? V raised to r. Or what is this r? And r is nothing but the ratio. R is the ratio of specific heat at constant pressure and constant volume. We had seen that in the previous class. Cv, Cp upon C. R is Cp upon Cv. Molar specific heat capacity at constant pressure, molar specific heat capacity at constant volume. So if this is constant for any adiabatic process, we know that P1 always equals to P2 V2, which will be a constant. Constant, I'll use the letter K. Now we will see what is the work done for a adiabatic process. For adiabatic process, no, like delta Q, anyways, there is no heat exchange, but volume, pressure, temperature always changes. No? So although delta Q is 0, volume, temperature, pressure can change. We had seen that under compression when you are releasing the piston and all, Obviously, volume will change, its temperature is either cooling down or heating up. These three changes. Volume can change, temperature can change, pressure can change. Only heat exchange is not taking place. So we'll do what is work done for in an adiabatic process. Work we know is pressure into volume. So for small work, okay, for a very small work means you are moving the piston slightly ahead. So what will happen? The change in the volume also will be very small. Work is nothing but moving of the piston. So if for a very small work means slightly if you are moving the piston means there will be very small volume change. So the equation will be, now if we calculate piece by piece like same like the previous derivation, the whole thing if you want to check the whole work, then we have to integrate. Now I told you P is not constant. P can change. As long as it can change, it is not to be taken out. Only if it's a constant, you can take it out of the integral sign. Now this is V and this is P. We cannot integrate with respect to P and this is V. The same letters has to be there. So now for adiabatic process, we have just seen what is the relation between P and V. PVR equals to constant. Constant means K. So what will be P? K upon VR. V raised to. So instead of P, now just put this. K is a constant. So this will be. Now this constant can always remove out. This will be W. Or before that, I'll just write dW. Now K. If it was single letter without any power, no answer would have been log. I told you 1 by x is always log x. But 1 upon x square is not log of x square. It is wrong. We cannot directly integrate, so we'll bring this power up first. So it will become v raised to minus r. The power, if we bring up, it will become minus r. Now it is in the form of this formula. X raised to n dx. Integral of x raised to n dx is always x raised to n plus 1 upon n plus 1. Now the value of n is anyways minus r. So as per the formula, it will be integral of 1 with respect to w will be w. Now as per the formula, this will be v raised to n plus 1 upon n plus 1. Okay, we'll just put the in this change is from one volume to another volume. Everywhere we just put v1 to v2. Volume is changing from v1 till v2. This will be okay. Now wherever there is v, you have to always substitute a higher limit minus lower limit. This is anyways constant, so we'll remove him out. Minus r plus 1 will be a pure number, so I'll write it as 1 minus r, and this will become v2, this will be v1. Higher limit minus your lower limit. Wherever there is this v, you have to substitute as v2 first. Middle sign is always minus, then you have to substitute the lower limit. Yeah, write it as 1 minus r also. Now we just multiply this k inside. I had given you all one equation just now for adiabatic change. P2 V2 raised to R is equals to K. So this also is equal, this also is equal. So instead of K here, I can put this. And instead of K here, I can put this. K I've already taken inside now, so this will be 1. No? I multiplied K inside. So I'll keep it out 1. Now instead of K, what I'll substitute? V1, V1. Oh, this is V2, no? So wherever there is V2, I'll put everything in terms of V2. And wherever there is V1, I'll put K in terms of V2. Everything 1, yeah, everything 2. I've replaced the values of K. So wherever there is 2, put K as this. Wherever there is 1, put K as this one. And there is this one, no? Minus R, or 1 minus R. Okay. This is of this part. This is already which is there. Now add the powers. Same thing, no? So P2, V2, R plus 1 minus R. This and this will cancel. All the powers. Same, this, no? Variable. So I can add the powers. So R and R will cancel. So what remains is P2, V2 minus V1, V1. This is in terms of volume. If you want, this will be answer, work done. In terms of pressure and volume. Suppose if I want to write in terms of temperature now, the same formula for work done. I can use this formula, PV is mu RT for an ideal gas. Of any normal gas also, you can use this. PV is mu RT in terms of temperature. So what will happen? V2 will be, this will be, mu R is anyway constant. So P2 will be mu RT2, this will be mu RT1. Don't change this because they are constant. Gas constant will always remain the same. Number of moles also, you will obviously take the same gas. So moles will not change and gas constant also will not change. Only for P1, V1, this will become T1, and for P2, V2, this will become P2. Again, mu R you can remove out. So this is the work done in terms of temperature. Some places you might find this formula. What they do, they are taking this, reversing the sign, minus. Then if you are reversing this, this will also reverse. Mu r, that making this r minus 1, then this you can take t1 minus t. Both are correct. Huh? Whichever you take will be same. Either you take, so what is basically they are doing is minus, if you take out common, here also minus, they are taking minus, minus will cancel. So you will get this. So this is work done for adiabatic process. Next one we'll see what's the isochoric process. These are simple ones, small ones. Just an explanation is there, no derivations, nothing. You know that isochoric process is a thermodynamic process done at constant value. Which occurs at constant volume. So if you see the graph, how it would look like, volume is constant. So only what will change? Volume is constant means V remains same. Pressure will change. Okay, or and temperature can also change. This remains the same. So if you try to plot, only pressure will change. So volume you are keeping fixed. Suppose volume is at 10. So it will remain at 10 only throughout. Only what is changing is your pressure. So from 5, 10, 20 maybe that is changed. But volume would always remain the same. So isochoric process graph will look like this. So what it means basically, if you are keeping volume same, means the piston is not moving 100%, because if the piston moves, obviously the volume is changing. It will increase or decrease. So if you are trying to keep volume same, means you are keeping piston fixed. Piston does not move. So piston is not moving means there is no work. No work is done on the gas. So there is no work done on the gas, nor the gas is doing any work on the piston. Okay. So over here, so which is, this is not moving. So there will be some heat supplied. Now this is not insulated and all. This is a different process. Adiabatic is insulated. Now this will be definitely some conducting work. So here there is heat supplied, because now this is not moving. So the only way to supply heat is external one. So whatever the gas is absorbed, Okay, the heat absorbed by the gas. I've told you all, the gas heat can be increased in two ways. One is by providing the outside heat or by doing the work. In adiabatic process, the previous one, heat was not supplied. The only thing which you could increase the temperature of the gas was by compression or expansion. Now over here, what we are doing, this we are keeping fixed. This nothing we are doing. The only way we are supplying heat to the gas is through this. So the heat absorbed by the gas is utilized. So where will this entire heat go? It is not able to push the piston because that is fixed. No work is done. So it is not losing any energy in pushing the piston. So the entire heat which it is absorbing is utilized, is used, you can say, entirely, means fully utilizing to change its internal energy and temperature. So what is happening? Whatever the gas is absorbing, it will only use in increasing its internal energy, and hence the temperature will rise. Piston will not move at all. If the piston was not fixed, some energy would be used to push the piston, some energy would be used to increase its temperature. So this process, where volume is kept constant and then the temperature is increased, that is called as a isochoric process. Last one is isobaric process. Thermodynamic process. Which occurs at constant pressure. Pressure is same. Now what can change? Okay, pressure remains same. Temperature and volume will change. Over here, there is some work done by the gas. Consider this situation. Consider if there was some weight. Okay, some weight was put on this, on the piston, and the gas was kept. Okay, but the piston is still movable, it's not fixed. Now suppose this gas is kept under, suppose 10 pascals pressure. Okay, consider the pressure on the gas is at 10 pascals. So I am not going to change the pressure at all. I have kept it at 10, fixed. Now there is heat supplied, but there is no restriction on the this. What is that? I'm not going to change whatever pressure was there initially. I've kept it fixed. I'm not going to change it. That much weight I've provided. I'm not adding any weight to increase the pressure on the gas. So I've maintained this at 10. Now suppose you start supplying this heat. So what is going to happen now? They will slowly get heated up. They will gain energy from this. So whenever any gas gets heated up, it expands. So when it expands, it will gas will expand. It will push the piston up. So that is nothing but called work done by the gas on the piston. So what is going to happen? It will push the piston up. So definitely volume changes from, suppose V1 it was to V2. Therefore, work done will be now what is given as pressure is constant. This is not changing now. V2 minus V1. So this is in terms of volume. Suppose if you want to know in terms of temperature, then you know that PV is mu RT. What I'll do is open up the bracket PV2 minus PV1. So work done will be mu RT2, same like adiabatic process we have done, mu RT1. Mu R you take out common. So in terms of temperature, this is the work done for isobaric process. Over there, what was work done? For isochoric, just write and keep on. For isochoric, no, just write and keep on. Work done I've given, anyway, no work done. So work done is 0. Why is it? Because work is, you know that, T into V2 minus V1 or delta V. So for isochoric process, you know that it is constant. Volume is constant. So volume will not change. So that's why work done will be 0 for isochoric process. There is no change in the volume. That's why no work. That is, the piston is not moving in the previous one. Here the piston is moving. Okay. And then in terms of temperature, this is the answer. So work done for all the processes I have given. So over here, what will happen? Now this is also working. Means some heat it is taking. Plus this is also happening. Movement, work is also done. Plus heat is gained from the external one. For this process, the heat absorbed by the gas is used to partly increase the internal energy and partly to do the work. So both things are taking place. It will gain the energy also, plus it will move the piston, means it will do the work also. Therefore, temperature changes. And how much change it takes place depends on the capacity of the gas. for a given amount of heat depends on specific how much capacity the gas can take. Okay, how much heat the gas can take. Depends on different gases. How much change in the temperature can occur at constant pressure. So these were the four processes. So if you want to know what is a cyclic process means it will come back to its original place from where it has started. Cyclic process, the process where the system returns back to its initial state. You will see this in further, like in the engines and all. If it goes, and it will come back also, back to its original place. There are various types like this also. So for this, internal energy is always 0 and Q will always be equal to your work. For isobaric, no? Isobaric, if you want to know the graph, just that small one you draw at the side and keep on. For isobaric, you know that what is constant? Pressure is constant. Volume will change. So this is the graph for isobaric. Isochoric, it was like this, no? The pressure was changing, volume was constant. Here, pressure will be constant, volume will be changed. If you want to compare all the graphs, all them not given for adiabatic and this, and draw now like this and so. Volume versus pressure. Vertical line is of whom? Isochoric. And is it as 1, this I'll use as 2. 3. I'll use straight away like this. Yeah. 1, 2, 3, 4. So 1 is graph of isochoric. Second one is of adiabatic. Third one is of isothermal. And the fourth one is of isobaric. Constant, no? Straight horizontal line. So these are how the graphs of different thermodynamic processes look like. Isothermal is a very slow process. It's almost constant. This adiabatic is quick. It will move faster. Changes will take place faster. You see the second law of thermodynamics. Now, what does the first law says? First law is dependent on conservation of energy. Conservation of energy means what? Energy can neither be destroyed nor can be created. So what does it try to say? Q is always delta U plus W. Means total work done plus this. There's nothing lost in the surrounding, nothing. Purely everything, whatever work plus internal energy is not equals to your heat supplied. Everything is getting utilized. Whatever Q you're supplying is its internal energy plus whatever work you're doing. Total is equals to this. That is your first law of thermodynamics, which says that is based on conservation of energy, that no energy is lost to the surrounding. But practically, they are all, this is all theoretical. But in practical life, like as per nature wise, not every process will work that way. So as per conservation of energy, what should happen? Any process which takes place from A to B, suppose, in order to conserve the energy, it should be back from B to A. That same energy I'm utilizing to change from something to something, that same energy if I'm using here, okay, I should be able to get back from B to A. Consider this, suppose I have suppose gas 1, I have gas 2. There is a different one. This is different. Now, suppose if I remove this wall, I remove this wall. So what is going to happen? Quickly, what will happen? All the gases will mix up. Okay, and now they all mixed up. They will reach at an equilibrium where no more mixture can take place. Now, as per this law, what it should work? Again, if I put back the wall, okay, it should work reverse also, no? So from here, now I want to try to put back the wall over here. Now it's everything mixed. Now, but will it try to all the gases go back to its place? No, it is not possible. Okay, it's not possible to reverse. So these are like this is like spontaneous reaction, the way it works. This is not, it will not happen until and unless you spend some extra energy on this to separate out the gases. Okay, whatever is there, it should, as per the law of conservation, it should have worked. But in practical life, it doesn't work. Same you can consider like one you have at 0 degree water, one at 100 degree. If you mix them, suppose if you mix, they might come to 50. Okay, but if you try to again now, same wall you put and remove the wall, all the water will get mixed up. So it will. So if you put back the water, can you again separate this 0 and this 50 on its own? No. On its own, it had got mixed up and came thermal equilibrium. But on its own, it is not coming back to what it was before. Okay, so this is what second law of thermodynamics tries to say. That is based on the nature law. Again, time also one more example. Time moves forward. Can you take it backwards? No. So something occurs in nature which doesn't follow first law of conservation of energy. The second law of thermodynamics tries to say that all work can be converted into heat, but all the heat cannot be converted back to work. Example, you just try to rub your hands. Okay, if you try to rub your hands, what will happen for a long time? Just keep rubbing, it will generate out some heat. So whatever work you're doing is getting converted into heat. But now is that same heat what was generated you use, can the heat make it work back? Okay, now you are rubbing it. Okay, so what will happen? Heat is generated. So some work you did, some heat got. Now same heat, if you try to put it on your hands, automatically will it make your hands rub on its own? No. So this is like trying to show that second law of thermodynamics. Work can be converted to heat, but that heat, if someone gives you to your hand, automatically you may not able to do that. Now, based on this law, we'll see how what is the heat engine. Normal day-to-day life, any of the engines like motorcycles, machineries, how they work. So what is a heat engine? It's a device that converts or that converts heat into work. So your car or your bike would have a heat engine. What is the work of the engine? Fuel. You give petrol or whatever, this, so the fuel is ignited. Then that whenever the fuel is burning, so it will give out heat. That heat will go into your engine, and then engine will do its work. Means basically it will make whatever system which makes the tires run. So that is nothing but the work. So your engine is taking the heat from the petrol or from the fuel and making the piston of the tires or whatever the shaft work. So normally heat, there is an engine, then it will give out to work. This I will not give because there's something else also. So I'll explain like this. There's always a source. Source means the fuel in your bike, suppose. If the source is generating the heat, consider it is at some temperature T1. Now it is giving out heat. So that will be Q1. So that will go to your engine. Now engine will do some work. So as per second law of thermodynamics, the entire heat will never be converted into work. Some and heat will always remain. Okay, any perfect engine will never be able to convert the entire heat into work. Some heat is always remaining. So that will take it as Q2. So half it is using work, half. So that remaining goes to something called as sink. So this is it is always also called as hot reservoir. Why? Because sink will always have a lower temperature than this reservoir, and this is a cold reservoir. Reservoir means it's a place. T1 is greater than T2. So this is a hotter reservoir than the sink. So what happens in an engine? heat is supplied from the source, heat Q1 you can say, from source to engine. Engine takes heat Q1 from source, does the work W and gives Q2 amount of heat to the sink or to the cold reservoir. T1 is greater than T2. So what is happening? Look at the equation. Q1 is what? Work done total. How much Q was supplied? Where it is gone? One is gone here, one is gone there. So this plus this was Q1. So what equation you will get? Q1 minus Q2 is work. Q2 you bring this side. Look at this equation. Total heat supplied was Q1. So it got splitted in two parts. W plus Q2. So Q1 minus Q2 is W. Now we'll see what is efficiency of an engine. So efficiency, this symbol it is given as work done upon heat supplied into 100, because efficiency is always given in terms of percentage. Percentage means so you have to multiply it by 100. So now as per the formula, what was the work done? Means as per the diagram, W was the work done, heat supplied was Q1. Work done by the engine was W. What was the heat supplied to it? Q1. From this equation, what is work done? Q1 minus Q2. Just distribute this. So this will be 100 is there. So you can write it this way also. Okay. Efficiency of any engine can never be 100%. Any engine can never be 100% efficient. Why? It is because it just see, look at this equation and see when can be it full 100%, when Q1 Q2 upon Q1 should be equals to 0, means basically when Q2 is 0. So I told you, can ever Q2 be 0? No, some energy is always lost. If Q2 was 0, then the second body was not needed only. There would be no comparison. Okay, if there was no sink, means what? This could work at any temperature. No reference is needed, no? If the second body is not there, suppose cold temperature. This would work at any temperature. It means basically, even without fuel also, if you give any temperature, it should have worked without the second thing, which is practically not possible. Okay, so what it is trying to say, suppose if you have a ship and there's a water, it is at suppose 30 degrees Celsius. So at any temperature with reference, it has no reference on the sink, no cold is there. So it means any temperature can be there. So basically it should be taking the energy from the engine, should be taking energy from the sea and not from the fuel then, which is not possible. Okay, so basically because Q2 cannot be 0. If Q2 is not 0 means something will get minus from 1 and it will become less than 100. Okay, similar logic, we'll see how the refrigerator works. From the this actually syllabus, refrigerator topic has been deleted, but I'll just do it's a small one. Your teachers skip that, you can just skip it. Even heat engine I think is deleted, but later that Carnot's engine is there. I don't know without that heat engine how they'll explain the Carnot's engine there. So anyways, I'm doing the concept. Now refrigerator little bit works ulta. What it does is same thing, engine is there in the middle, same hot reservoir. This is the cold reservoir. Only thing now what is happening? Who is the source here? This one, cold. Why? This is suppose the fridge inside. It is always cold. Now suppose if there is some heat which it is getting, you put something in the fridge. Now its temperature will slightly increase. It got some heat to remove out from the food. To keep some food here. Now it has to remove out the heat. So that heat will come here. That is Q1. Now, is this heat from the food sufficient to make the engine work? Is this heat from the what is that free food, what it is giving out, is it sufficient? No, 100% no. You can name this as Q2 only. Okay, but only thing is going reverse. Now this heat is from the food which is not able to drive the engine. So what you need? You need extra outer work. So that is nothing but the electricity. So you need this work also for an engine to move. And then it will cool out whatever it is and give it back to this hot reservoir, means to the atmosphere. This is like an atmosphere outside your fridge. So So what it's basically doing is it's taking the heat from the food, but in order to this, for the engine to work, there's an external supply also, because this is not enough. And then whatever heat it is given out. We can write a refrigerator is reverse of a heat engine. Here you may not use the word engine, put something else otherwise. You can say the word compressor, whatever, some working substance might be there. Okay, you may not use the word exactly engine, because refrigerator might not have actual engine as such. Anything that compressor, we don't want to know too much in detail. The compressor part, whichever helps in cooling down the fridge and all, that might be the one. So we'll use the word working substance. The working substance extracts means takes the heat Q2 from the cold reservoir this is the word T2 at temperature T2 some external work W is done on the working substance. Okay, heat Q1 is released to the hot reservoir. You can write to the atmosphere, that is outside the fridge. Obviously, if you see, your atmosphere will be at a higher temperature than your fridge. Temperature inside the fridge is obviously less than the atmosphere. Okay, so this is how a refrigerator works. Same way, the refrigerator, there's something called as a heat pump. Heat pump is like the heater which you use to heat up the rooms, no? So only difference here will be the hot reservoir, no? Will be a room which needs to be heated up. Room or any space, okay? Or your car also, if you want to heat up in your car, if it's very cold outside and you just want to maintain the heat inside, so that will be this. So room which needs to be heated up. What is going to happen? This will be a working substance. That could be the condenser, whatever. And this is your environment. That will be a cold reservoir. When it is needed, heater is needed when the outside atmosphere is very cold and you want to make it your room hot. Okay, outside it's very cold. So this will be your atmosphere now. It's picking up some heat Q2, doing some external work. And then this Q1 is more, obviously. This entire work is also getting converted into heat. This is very small actually, because already it is cold. Very small amount of heat. This will be large amount. So work plus the small heat gets converted into a larger heat, which will go to the hot reservoir, which helps you to heat up the room. It's same like refrigerator only. Only what difference it is, instead of the atmosphere, this is the room. The cold reservoir. Now you know it is an atmosphere. Q2. External work W is done on the working substance. Same, this only have to explain, like refrigerator. Heat Q1 is supplied to the hot reservoir. That is your room or a space, any space which needs to be heated. Okay, for both the, you can write what is the this this would be there's something called as coefficient of performance. Given as alpha, so it is nothing but Q2 upon W. So W is always Q1 minus Q2. Nothing but the heat supplied upon the work done. Okay. That Carnot's engine is slightly big, so that I'll anyways do it in the next class. I'll stop here.